Okay, so in this lesson, we are determining unknown chemicals. Now, there's a lot of technology involved here, which I'm not going to talk about. These are something that hopefully you guys can read upon. So the three things, okay, that we're going to be talking about in this lesson is how to determine unknown hydrates. 2, how to determine empirical and molecular formula given percent composition. And 3, combustion analysis based on mass of products. So we're going to look at each one by one, of course starting with hydrates. The question is, what are hydrates? Most chemicals that you see in the labs are in the form of hydrates. For example, copper 2 sulfate is something that you guys use a lot. It is the blue crystal. But what you don't know is that the one that you have in your lab are usually in some sort of hydrated form. Now, we've seen this with nomenclature, where copper 2 sulfate may have a formula that says CuSO4 dot 3H2O. This will be the hydrated form of copper 2 sulfate. And to name this is called copper 2 sulfate trihydrate. What that means is that you have copper 2 sulfate, and this is bonded to 3 water molecule. Okay? However, what if I don't bond it to no water molecule? I just have CuSO4 the way it is. What would this be called? Well, the word here is called anhydrous. So this will be the anhydrous form of copper 2 sulfate. All right? And I have a question here. And this question, you are going to be asked to find the number of hydrates in copper 2 sulfate. So here's a question right here. Okay. I have 0.28 grams of copper 2 sulfate, something hydrate. Oh my goodness, I need to know what that something is. Okay, I have 0.28 grams of copper 2 sulfate, something hydrate. What happened is this. I heated this up. By heating it up, I'm driving, I guess, some of the water off. So what I have is copper sulfate anhydrous, and I have 0.1789 grams of it. So obviously what happened here is 0.28 grams of copper 2 sulfate, something hydrate. Some of the water got evaporated. How much? Well, 0.1011 grams of water was evaporated. Because what I have left is some sort of anhydrous copper sulfate that is 0.1789 grams. So most likely 0.1011 grams of water was driven off and evaporated. Okay? That's something good to know because we will need to use that number later, because the formula to calculate hydrates is very simple. X is equal to moles of water divided by moles of anhydrous. Now, if you think about it, hey, dividing, hey, there's ratio involved, right? Exactly. This is all about ratios. Check out this. What does this mean? This is really a ratio.
Do I look zombie enough? I'm not scaring me.
Looks so real.
Are you gaming on a Chromebook?
Yeah.
Go ahead, break it down real low. Stop playing with it. Red light, green light, go.
Aveda.
That for every mole of copper sulfate, it's hooked up to 3 moles of water. That's what it is. So the mole ratio here is 1 to 3. These are experimental values that you actually did. You took 0.28 grams of copper 2 sulfate, something hydrate. You heated it up. You evaporated the water out of this. Because what you have left is this amount of copper 2 sulfate. To find out what this is, I apply this formula. So let's apply this formula. Okay, so let's find mole of water. Well, I just said, of course, the number of water driven off is the difference of these two masses. And what it was 0.1011 grams of water that was driven off. And if you would divide that by the mole of water, because that's how you find molar mass. That's how you find moles, right? Moles divided by molar mass. And you really do the same thing with anhydrous. So 0.1789 grams of anhydrous. And you turn that to moles. Okay, so that will be 64. Copper, I think, is 64 plus 32 plus 16 4 times. Okay, so that's 160 grams per mole. What would that be? So 0.1011 divided by 18. That's 0.0056 mole over 0.1789 divided by 160, which is 0.0011 mole. So again, if you divide the two numbers, you should get some sort of integer. And that integer is 5. At least you round it to an integer. So the answer is CuSO4, 5H2O, pentahydrate. So that's how you find hydrates. Okay? Given a hydrated salt, you heat it up, so you drive all the water off. So you end up with an anhydrous salt. Divide the mole of water driven off by the mole of anhydrous. You should get the ratio of your salt with the number of hydrates. In this case, is 5. Right? So, hopefully you guys are, I guess, somewhat happy about that. But that's exactly how you find hydrates. Okay? Alright, let's take a look at the second item here. The second item is based on empirical and molecular formula. Okay? Given percent composition. So let me do an example. I have, let's say, 80% carbon, 20% hydrogen. So you know that this works out because the sum of the two add up to be 100%. Now, I don't really have to use percent. I can just use grams. But that's exactly what we're going to do. We're going to turn these percent, or we're going to assume these percentage as mass. Okay. So the molar mass here is 30 grams. That is something that, a mass spectrometer will tell you. And the 80% and the 20% carbon and hydrogen, respectively, are usually given by this machine called gas chromatography. Chromatographer, I don't know. Okay? But together, we call that GCMS. With this information, you can find the empirical formula and molecular formula. So let's take a look at how we're going to do this. Okay, let's take a look at how we're going to do this. Now, what I've written there, of course, is glucose is the molecular formula. Okay, that's the true formula. That's sugar. But if you were to put this into empirical formula really means the reduced version. So the reduced version of C6H12O6 is C1H2O1. Now you just reduce the ratio of 6 to 12 to 6 to its reduced form, 1 to 2 to 1. So in this question, I want to know how many C's and how many H's based on 80% C, okay, 20% H. So let's go. Okay, let's find out C what H what, given the molar mass to be 30 grams per mole. Let's take a look at empirical formula first. And then, of course, we will look at how to get molecular formula out of the empirical formula. All right, let's get to work. So first, let's take a look at the percent composition. Well, we've seen percent composition before. Okay, so with this, we are able to find the empirical formula. So let's take a look at how to do this. So assume that 80% is 80 grams. I mean, it's a cheesy assumption, but that's the way it is. You don't want to turn that into a decimal. You can, but you'll be working with very small numbers. Not a fan of small numbers. So first, turn 80 grams of carbon into mole of carbon by dividing it by 12. Turn 20 grams of hydrogen to mole of hydrogen by dividing it by 1. As a result, hydrogen, you have 20 moles. Now that's easy. For carbon, let me bust out my calculator here. 6.67 mole. All right. Now that you turn C into mole, H into mole, now we're ready to do some mole ratios. Now, hopefully you remember how to do ratios. So let's do some ratios. So look at the two numbers. Which one is smaller? That's pretty obvious. It's 6.67. So you're going to divide both number by 6.67. Why? Because you want to set the lower mole to be 1. At least for now. Let's do the division. What would H be? 2.99. All right. That is close enough to be 3. Now, hey, is it always roundable like that? No, it's not. You can't always just round. If that number lies between 0.25 to 0.75, don't round. Don't round. You're going to have to do something else. What that something else is that you're going to have to multiply both moles by increment integers. Okay? But in this case, we're lucky enough. We're lucky enough that 2.99 was a roundable number to be 3. So if you have 3.26, hey, that ain't 3. Ain't 3, man. Ain't 3. If you have 3.74, I mean, that lies between the two numbers. That ain't 4. Ain't 4. So be careful here. Okay? So make sure when you're doing your mole ratios, don't just round like you do in math. Like you do in finite math. That's not going to happen. So let's just say this was 1.33, okay? And that's 1.33. Can you round that to 1? No, of course not. It's between 0.25 to 0.75. Can't see that's a 1. So what do? Times 2. So carbon will be 2. Hydrogen will be 2.66. Is 2.66 a roundable number? No, that's not a roundable number. Again, that's between that limit. So we can't do this. We have to do something else. Let's times 3. So if you times 3, carbon will be 3. Hydrogen will be 3.99. Now that is a roundable number. That's a 4. I'm pretty sure all of y'all, agree with me. That's a 4. So the ratio of C and H is 3 to 4. If it is 1 and 1.33. Okay? So don't just round anything. Not anything. No, there's a little limit of tolerance or intolerance here. So let's go back to this question. Okay? So the ratio was 1 to 3, which means that the empirical formula here is basically C1H3. All right? CH3. Yeah. You don't say the 1. I've never seen people write C1H3. That will be ridiculous to acknowledge the 1. CH3. Okay, that's the empirical formula. Now let me ask you, is that an actual compound? I don't think so. Okay. All right, let's take a look at how to find molecular formula. So as I circled earlier, the 30 grams per mole of molar mass that you get from the mass spectrometer means something, because we need to find something called the N value. Now, the formula of this is molar mass divided by empirical mass. Now, what is the empirical mass? Empirical mass is basically the molar mass of the empirical formula. Okay? So the molar mass is given as 30 by the mass spectrometer, and the empirical mass we can easily calculate by looking at the empirical formula. 1C, 3 H's. So that's 12 plus 1 plus 1 plus 1. Okay, and we all agree that will be 15 grams per mole. Hey, divide that number, you get 2. Now, let's say it has decimal, and when you're dividing, you can easily have decimals. Again, the rounding rule apply here too. Okay, so if you have something like 2.5, don't round that to 3. That ain't 3. Multiply that by 2, because that's 5. All right? Again, no rounding between 0.25 to 0.75. But luckily it's a 2. So that means this N value is a good value. We don't have to multiply by anything. You know what I mean. Okay, so what are we going to do with this 2 that we got as an N value? Well, you're going to multiply that by every member in your empirical formula, CH3. So the idea here is going to be 2 times C and 2 times the amount of H's. So that becomes C2H6. Hey, C2H6, if you know anything about organic chemistry, that is called ethane. Okay? It's a 2-carbon hydrocarbon. It's a gas. So there it is. This is how you find empirical and molecular formula. So given percent composition, given molar mass, you are able, of course, to find mole ratio. And of course, using the formula for N, you are able to find the molecular formula. So make sure you try some of those practice questions I have for you. All right, the third one. Oh, this one is a big one. This is combustion analysis. Now, what are you given here? Okay, you are given mass of reactants and products. Combustion. First, let's think about what is combustion. Combustion is when you are reacting with oxygen. If you're looking at a fuel, let's say this fuel is called CXHYNOZ. Okay? And let's just say I have 1 gram of that. Okay, I have 1 gram of this unknown fuel. All right? So I need to know what's X, what's Y, and what's Z. So I took 1 gram of this fuel. It doesn't always have to be fuel. This could easily be sugar. But, sugar is a fuel. This could also be alcohol. I mean, alcohol can be a fuel too. So when you're combusting, you're reacting with oxygen. Since this is a organic fuel, what you're going to get out of this is carbon dioxide and water. A simple, complete combustion reaction. All right. Let's see here. 1 gram of CxHyOZ reacting with oxygen, and inside a closed vessel, we are able to collect 1.5 grams of carbon dioxide and 0.405 grams of water. Okay. So with 1 gram of this fuel and reacting with the oxygen in the air, which we can find out what that is, but really is unnecessary, we are able to produce 1.5 grams of CO2 and 0.405 grams of H2O. Now, this is all the information that you need to find the empirical formula for CxHyOZ. But let's say we also did a mass analysis, and we know that CxHyOZ was worth 352 grams per mole. Let's say we did that analysis also. Okay, so let's find empirical formula first, and then we're going to find N to find molecular formula. So let's take a look at this 1.5 of carbon dioxide. Now, this is something that we've done in previous lessons before. We want to find how much carbon in carbon dioxide was the carbon in the fuel. Because if you think about it, all the C in the fuel went on to become C in carbon dioxide, right? So if we can find in 1.5 grams of carbon dioxide, how much of that 1.5 gram belongs to carbon, we would know that out of 1 gram of fuel, how much of that 1 gram belongs to carbon as well, because all the carbon in that fuel went on to become carbon of carbon dioxide. So let's do this. We know how to do this. So out of 1.5 grams of carbon dioxide, okay, how much of that 1.5 gram belongs to carbon? So we multiply by the percent composition, which is 12 grams per mole of carbon over 44 grams per mole of carbon dioxide. Okay, because carbon is 12 grams per mole, carbon dioxide is 44 grams per mole. All right, grams per mole and grams per mole cancels. Carbon dioxide and carbon dioxide cancel. So you're left with grams of carbon as your final unit. So let's take a look at what that is. So that's 1.5 times 12 divided by 44. Okay, so in 1.5 grams of carbon dioxide, 0.41 grams of it belongs to carbon. Now, what that also means is that 1 gram of fuel, 0.41 grams of it also belongs to carbon, because all the carbon from the fuel went on to become the carbon in carbon dioxide. So let's do the same with water now. Let's take a look at hydrogen. So with 0.405 grams of water, how much of that belongs to H? Now, be careful here, because there's 2 H's, okay? Unlike carbon dioxide earlier, there's only 1 carbon in carbon dioxide, but here there's 2 hydrogen in water. So I'm pretty sure you guys can tell me that all the H's from the fuel went on to become H's in water. So let's find this out. So with 0.405 grams of water, okay, how much of that 0.405 grams belongs to hydrogen? So let's do the same thing. Okay, so the molar mass here, of course, is 2 times 1 grams per mole is hydrogen over 18 grams per mole of water. Okay, so remember, there's one carbon earlier, but then there's 2 hydrogen in water. That's why we multiply by 2. All right, let's cross out some units. Okay. Grams per mole and grams per mole can cancel. Water and water cancel, so you're left with grams of H. So if you do the math, that is just 0.045 grams of H. So out of 0.405 grams of water, 0.045 grams of it belongs to hydrogen. Again, what that means is that 0.045 grams of H is also part of that 1 gram of fuel. Okay, so carbon, all the carbon from carbon dioxide went on to become carbon. Sorry, the carbon of the fuel went on to become carbon dioxide, and the hydrogen of the fuel went on to become water. So we can link that back. Hey, so we know how much carbon is in the fuel. We know how much hydrogen was in the fuel. The only thing left is oxygen. How much of that oxygen is in the fuel? Well, it's very simple. We are given the mass of this, right? We're not going to look at how much oxygen is in carbon dioxide plus how much oxygen is in water, because that will be a lot of work. So instead, let's save the work. We have 1 gram of fuel. Okay, we have 1 gram of fuel. We already know how much of that is a carbon. We already know how much of that was hydrogen. Now, we should be able to find out how much of it belongs to oxygen. Or in other words, the rest of it belongs to oxygen. So let's do this. So 1 gram minus the sum of 0.41 grams plus 0.045 grams. This will give you the mass of oxygen in 1 gram of fuel. Okay, this is 0.545 grams of oxygen. Hey, look at this question. Look at this. Now we have mass of all 3 participants that makes up fuel. Doesn't this look just like one of those regular questions we solved 10 minutes ago? Okay, with empirical formula analysis, right? It's just the last time we looked at percent, but we turned those percent into mass anyways. So here we are directly given mass of C, mass of H, and mass of O. So what we need to do now is turn them all into moles by dividing carbon by 12, by dividing hydrogen by 1, and dividing oxygen by 16. So let's take a look at what they are. So 0.41 divided by 12. All right, it's 0.034 mole. 0.045 divided by 1, that's easy. Okay. And 0.545 divided by 16. What would that be? Okay, 0.034 mole. Okay, we turned them all to moles. If you remember, the sequence is now you look at their ratios. You looked at what is the smallest number. Well, the smallest number is 0.034. So we're going to divide everybody by 0.034. So the ratio is 1 for carbon, 1 for oxygen. Hopefully I get a nice number. 1.3. Dang, I don't have a nice number. 1.3. All right. Well, I guess we do know what to do. Okay, we can't say hydrogen is 1. 1.3 cannot be round to 1. We mentioned this many times. So we're going to have to do some multiplication. We are going to multiply everybody by 3. Because by doing that, Carbon is 3. Hydrogen is 4. And oxygen is 3. Okay. Oh, hydrogen was 3.99. I mean, that you can round that to 4. That's, outside of that limit of tolerance. Actually, it's limits of intolerance. So the empirical formula here is C3H4O3. Now, as I said, this is not the real formula. This is EF. This is empirical formula. This is the reduced form of what it really is. Now we need to find N. Take the molar mass, which is 352, that was given, and divide that by the empirical molar mass. Let me figure out what this is. 3 times 12 plus 4 plus 3 times 16, that's 88. Okay, so you're going to divide 352 by 88, and your magic number is 3.4. Okay, your magic number is 4. So, what are you going to do with this 4? You're going to multiply that by every member of this empirical formula. And your final answer for molecular formula is C12H16O12. So the fuel is that. Now, I don't really remember what this is. Name of this compound. I mean, it really doesn't matter. That's not the point here. I'm sure it's powerful. Okay? So, hey, that's how you determine unknown chemicals. So we looked at hydrates today. Okay? We looked at empirical and molecular formulas. Okay? Given, of course, percent composition. We looked at combustion through combustion analysis, which is what we did here. It's a lot of math. It's a lot of math indeed. But with some practice, I'm sure you guys are all good. I'm sure you guys will be just fine. All right. Time to go. Later.